Hello there and welcome to Chapter 8. We are going to have a chance to learn all about gas behavior in this chapter, which should be a lot of fun. Gas behavior is kind of fun and real and hands-on, so let's get started. The first thing we should talk about is pressure. What is pressure? If you think about this for a minute, and I'm not talking about like the pressure from all of your homework, right? I get that, but that's not the kind of pressure we're talking about. Physical pressure is defined as a force divided over an area. Okay, so pressure equals force per area. And one of the units that's common in the United States is PSI, which stands for pounds per square inch, which literally is a force of pounds per every square inch of area. We will not use PSI in this class, but I mention it nonetheless. Pressure is typically measured using a device called a barometer. You will read about this in the beginning of the chapter. The early barometers that were made by the scientist known as Torricelli were a very long glass tube, empty of all substances, including air, that was filled with mercury and then inverted into a dish of mercury. Mercury is a very dense liquid, and so the mercury would settle in the tube at a height of 760 millimeters tall. This is the distance between the surface in the dish and the level in the tube. Okay, and it was in fact the pressure of the atmosphere outside, pressure of the air, that was pushing the mercury up this tube and not allowing it to fall into the dish. Okay, so originally the height of the mercury was measured, and that was an actual pressure unit. If the pressure of the air went up, the mercury column went higher, and vice versa. And so this was a very useful way of measuring pressure. These are the three typical pressure units that we will use. As I mentioned on the previous screen, 760 millimeters of pressure, also called standard pressure, because at sea level, the height of the mercury column essentially averaged to about 760 millimeters high, is equal also to 760 torr. This is a unit named after Torricelli. So if I say 760 millimeters of mercury or 760 torr, that's exactly the same measurement. Another pressure scale has units of atmospheres, abbreviated ATM, and standard pressure is equal to the force of 1 atmosphere pressing down on us. These can be used as conversions to go between pressure units. Here's an example of 3 pressure conversion problems. So I'd ask that you pause the video and see if you can set up these conversions using the equalities on the previous page. Here are my 3 setups for these. You will notice the unit conversion that happens in each case. And so the rules of setting up conversion factors that you learned earlier in the course are still valid. And here you have the converted values. Now I'm sure all of you have perhaps flown in a plane or driven up a very tall hill or mountainside and notice that your ears pop when you do that. That's caused by pressure changes. So how does pressure change with altitude? Do you know the answer to that question? Think about that for a moment. If you consider yourself standing on the surface of the earth, you have above your head a very large column of gases called our atmosphere that are pressing down on you, pulled towards the earth by gravity. And that's what creates air pressure. If, however, you were standing on a mountain, the air pressure above your head decreases because there's a much smaller column of air above you. And so with altitude, air pressure decreases. The same would be true if you were traveling in a plane. The pressure definitely goes down at high altitudes. When we do calculations in this chapter, we will be manipulating the 4 variables that allow us to describe a gas. One of them is pressure, P. T is another one. That's temperature, as I'm sure you could predict. V is volume. And N is the letter we use for the number of moles of a gas. One detail before we continue: temperature must always be measured in the Kelvin scale when we're doing gas law calculations. Technically, we should always use the Kelvin scale, but in gas laws, it is absolutely required. You may remember that we can calculate Kelvin by adding 273 to a Celsius temperature. Note there is no degree sign on Kelvin, just K, capital K. Everybody knows what that means. So let's take a look at the relationship between pressure and volume. We're going to be assuming that moles and temperature are held constant. We're going to explore these in pairs, not with all 4 things changing at once. And I think the easiest way to picture this is envisioning something like a tire pump or a piston. Okay? If we push down, we can increase the pressure on the gas. Okay? So as pressure increases, what's going to happen to the volume of the gas? The volume is going to decrease. Okay? And evidence for this would be the fact that the piston moves down to a lower spot. I don't know how I can draw this necessarily. Try it this way. And if I move the piston down this far, then all of those molecules, of which there are 9, would be in a much smaller area, and they would be exerting a greater force on a smaller area. Actually, the same force on a smaller area. So the area decreases and the pressure increases. This is an inverse relationship. As one variable increases, the other decreases. And one way to write this equation would be to say that pressure times volume is a constant. As pressure increases, volume decreases, but they would equal a constant value. Sometimes we call that constant K. Now let's consider the relationship between pressure and temperature, assuming that, moles and volume are held constant. Okay, so we're envisioning a rigid tank. And if I had that rigid tank at, let's say, 20 degrees Celsius, there would be a certain amount of pressure caused by the particles as they move in the container, colliding with one another and the walls of the container. Okay? And so we would get pressure. However, if we increase the temperature, the area of the container, the volume of the container has not changed. However, the particles are now moving faster, and so they are going to exert a greater force on the same area, resulting in a higher pressure. So pressure will also increase. This is a direct proportion, and this equation could be written as pressure divided by temperature equals a constant. That's the nature of a direct proportion. Now, if we try to compare or take a look at what happens with moles and pressure, assuming volume and temperature are constant, again, a rigid container is probably the best to consider because the volume will not be changing. I'm going to ignore any change in the particle motion. Here's a container that has some number of particles in it. If I increase the number of particles by adding more moles, in this case I've doubled the number of moles, add more moles, then the pressure is also going to increase because I have a greater force due to more collisions on the same area. This is also a direct relationship, and we can write the relationship this way: volume over temperature equals a constant. So as you can see, there are quite a few relationships here for pairs of variables. The interesting thing, though, is I can combine all of these relationships, and we've only talked about 3 of them, and that's all we're going to talk about, into a single equation that is called the combined gas law, and this is how it is written. Pressure times volume divided by moles times temperature before something changes is equal to pressure times volume divided by moles times temperature after a change. Keep in mind, as far as units go, pressure, volume can have any units as long as they agree on both sides of the equation. N is in moles, and then T must be in Kelvin. This is really the only gas equation that you need to sort of commit to memory or have in a prominent place in your notes. At least so far. So let's take a look at how we can apply this equation to a couple of quick examples, and then we'll do some more in class. Pause the video and read over the question. That is this question right here toward the toward the bottom. There you go. Because there is no mention of N and no mention of V, no, there is, sorry, and no mention of P, we're going to assume that those 2 variables are constant. Okay, it's not necessarily going to explicitly state that, but that's the conclusion we're going to draw. Start by writing the combined gas equation and cancel out moles and cancel out pressure because those variables are constant and will not alter the mathematics. That reduces my equation to V1 over T1 equals V2 over T2. Now let's identify the given information. 25 milliliters is V1. T1 is 50 degrees Celsius. This is T2, and we are looking for V2. So I tend to rearrange the algebra before I plug the numbers in. That gives me the following equation: V1 times T2 over T1 equals V2. You're going to do the same algebra either way. Keep in mind that milliliters is a perfectly fine value for a unit on volume, but Celsius is not compatible, so we need to convert both temperatures to Kelvin. There are my converted temperature values. Now let's plug into the equation. You can see that the units cancel properly. I will get a milliliter answer, which is exactly what I'm looking for. And the answer will be 31 milliliters for V2. One last example in this lesson. Read the question, see what you can do to rearrange the equation, identify the given information. In this case, we will be assuming that there are 2 variables that are constant again. And then you can restart to see how I worked it out. So here I've identified the information given. A little bit of a trick here that to find the N2 value, you have to add the original moles and what moles were added. That doesn't always happen that way, but I think you can see why I had to do that. And here we are. I hope this makes sense. We will do more practice in class. Thanks for watching, guys.